So let's take a look at this pulsed ND YAG welder. This was a very popular laser for doing welding, particularly in the aerospace industry. What we're seeing now is fiber lasers starting to take over some of this work, but these big pulse YAGs are still very common, and we see them often. So we have all the information loaded in here. Let's just go down through it. We're going to be using the wavelength in nanometers. We have 1064 nanometers is the wavelength. We're repetitive pulse. In selecting repetitive pulse, we have some options here. We could enter average power, peak power, or energy per pulse. And all three of these can become useful when you're doing an analysis based on the information you're given, particularly if you're pulling information off a manufacturer's data sheet. The most common two, of course, are average power and then energy per pulse, but sometimes it becomes necessary to use peak power because they'll offer you the maximum peak power, and you want to use that to kind of compare and see which way might be the give you the most conservative analysis between looking at average power or energy per pulse. Sometimes we use peak power that way. All right, so we have energy per pulse in this case. It's 10 joules, 2 millisecond pulse duration, and this is a very common pulse duration for pulse welding. If you had a laser like this and it was half a millisecond or under, it would be used for drilling. We have a repetition rate, pulse repetition rate of 10 hertz. We're using the ANSI default exposure duration of 10 seconds, 1 over E squared, circular Gaussian. The beam diameter is 5 millimeters, and the beam divergence is 4 milliradians. And this is a pretty high m squared value, which is typical for one of these type of units. We can see that our OD at observer range at a half a meter is 5.47, very close to our worst case OD, not ID, OD. Let's go over here and take a look and see that that's where this difference is coming from, the fact that we're only putting 97%, about 97% of the power or energy passing through the limiting aperture of 7 millimeters. So that's where the difference between these two values come from. We have an NOHD of 1.37 kilometers or 1,370 meters. Let's look at our NSHD, and that is almost 40 meters. So the difference there between the NSHD and the NOHD is, of course, the difference in the MPEs. Also, a difference in the limiting apertures used, but it's mostly in these MPEs. This can provide a little bit of difference. This is the big difference. So we have an ocular MPE of 8.51 times 10 to the minus 4th watts per square centimeter, or 0.85 milliwatts per square centimeter. Skin MPE is 1 watt per square centimeter. The times MPE is almost 600 times the skin MPE is the irradiance of the laser. So is this a skin hazard? Absolutely. It is a major skin hazard. Again, if you haven't heard this already, 1064 penetrates the deepest, so you can get up to a 5 millimeter penetration into the skin. Of course, you're absorbing in a larger volume, so you don't get quite as much of a reaction to the same power level as if you were absorbing right on the surface. But you have to understand, at 600 times, you're going to get quite a burn, and it's going to be deep. Okay, so yeah, skin MPE 600 times, that's a significant skin hazard. And again, a laser like this will certainly burn something like, if you put some material in front of it, it can easily ignite the material. Okay, so let's go over here and look at our diffuse reflection, because in this with this particular laser, we are very concerned about diffuse reflection. This is a welding laser, so we're going to have energy being scattered off from the weld. If you lose the welding coupling, we can take a look at the numbers here for worst case, 100% spectral reflectivity, meaning all the energy is coming off the diffuse reflection material, or where it's being diffusely reflected. We have a viewing angle of 0 degrees, so that means we're looking at our most conservative case here. We're going to keep it a small beam on target so that we stay with the point source, which is our most conservative result between point and extended. Our observer range is 1/4 of a meter, and we'll stick with the exposure duration for diffuse reflection of 600 seconds. The MPE for 600 seconds and 10 seconds is the same, so that's why our intrabeam ocular MPE and our diffuse ocular MPE are the same. We see we have a point source NHC of 1.9 meters, almost 2 meters. So you can see this is a laser like this with this kind of pulse has quite a diffuse reflection hazard. The OD at observer range is about 1.8. The skin NHC is, well, it's not too bad. A little over 5.5 centimeters. So it's not much of a skin diffuse reflection hazard. Our MPE is the same as the intrabeam MPE, and you can see that we're well under 1 here, so that that tells us, again, no skin hazard from a diffuse reflection. Now, more likely is that you reflect some of the energy off of the weld. Even though you're coupling in and you're doing the welding, you'll reflect some of the energy off. So let's take a look at something a little different. Let's look at 20% here, and something more realistic to the angle, instead of looking at that straight on, which you really probably wouldn't be in the position to do. Might be maybe like 60 degrees. And we can see that, yeah, there's a bit of a change there. Instead of having almost a 2 meter NHC, it's down to about 0.6 of a meter. The OD at observer range is 0.77, or almost 0.8. So you can see there is a little bit of difference, and this would be a more typical value of what you'd see coming off of welding in terms of scattered energy or scattered power. Okay, let's take a look over here at our repetitive pulse information. You can see that now we have 2 MPEs we're looking at, and that's because we have 2 exposure conditions that we need to consider. The first one being the pulse duration, which is 2 milliseconds. And so this rule 1 MPE is based off of the pulse duration. The rule 2 MPE is based off the total exposure duration, which in the standard we refer to as T max, and that's 10 seconds. Now, what we do here is we convert the Rule 2 MPE to a single pulse MPE. We take the MPE that we get out of the ANSI standard and in joules per square centimeter, and it has to be in joules per square centimeter because we want to compare apples to apples, and the Rule 1 will be in joules per square centimeter. So we get the Rule 2 MPE, we get it into joules per square centimeter, then we divide it by the number of pulses in the exposure, which would be 100. And what we're doing is we're taking that total MPE energy, if you will, from Rule 2, from the 10-second exposure duration, and we're seeing how much of that is being given to a 1 pulse of all the pulses in the exposure, and then we can compare these 2 rules. Then we're really comparing apples to apples, and that's what we do. And we can see that we're comparing these 2 MPEs directly, and that the Rule 1 MPE is the more restrictive, and that's the one the system has selected. We can see over here that it looks like that's about the same MPE. Of course, this is in watts per square centimeter. So how do we go from here to here? Well, we take this MPE and we multiply it by the pulse repetition rate. Of course, we can switch this to watts and see, yes, in fact, that's where it is. Okay, so now these are being compared in irradiance, in watts per square centimeter. Let's click this back. We can also see, if we want to, what these would look like, what both of these rules give us in terms, or both of these MPEs, both rules with their associated MPEs give us for AELs. Remember that we take the MPE, multiply it by the area of the limiting aperture to get the AEL. We can click right here and get that. So we get the AELs in watts, okay, and we can make sure those two do agree with each other, all right, or we can get them in joules, either way, okay. So we'll put this back to joules, put this back to MPE. Now, one other thing I'd like to point out here is, maybe two other things before we get going. I forgot the laser source calculated values. You can always look down here and get some of the laser source calculated values, like the average power. We can see that we have an energy of 10 joules. We're running 10 pulses, and that should give us 10 times 10, 100 watts of average power. And then our peak power comes from taking the energy of the pulse and dividing it by the pulse duration, and that's how we get the 5 kilowatts of peak power in the pulse. We can see, of course, the energy per pulse we already know, but this also tells us the duty cycle. In other words, how long the laser is on versus its off time. So you have a pulse fire, and then we're off for a while, then the next pulse fires. The pulse on is the on time of the laser. The time between the pulses is the off time. We take a look at that, and you can see that the laser is running a 2% duty cycle. Now, you can look at this separately if you'd like to, and I just want to point that out because that's really what's going on. This system is, the software is taking this and looking at each situation separately. It's looking at the pulse, and then it's looking at the average power. So we could come up here and say, well, let me make this a single pulse. Okay, I have 10 joules, and I have a 2 millisecond pulse. All right. And you can see we get the same ODs, same NOHD, because, remember, these values, these calculated values, are based off of that Rule 1. So it's really telling you, it's basing it off the pulse. We can look at this, we can look at the second part of this by changing to continuous wave, keep our 10 seconds, go to an average power. Remember, our calculated average power was 100 watts. Let's take a look at that. And you can see that, yes, the average power from this, if we just look at the 100 watts, is less than what's happening in the pulse. So really, we could even if we had just a continuous wave and single pulse, we could still analyze this problem. But being able to look at it all at once using repetitive pulse, and the software tells us what's going on and then decides which is the more hazardous condition. Is it the pulse or is it the average power? So it does it for us automatically. So let's go back and, I'll show you one other thing, what I could have done here. Let's go back and put the repetitive pulse information in. And I wouldn't have had to put this back in. I'll just show you this quickly while we're sitting here. And I'll put that back as 10 hertz. So everything is back. What's wrong? Oh, energy per pulse. Yeah, see, I looked at this and went, whoa, what is that? It looks like about 10 times over. And that's because we just left 100 in for the energy. So let me put that back. Had I wanted to change that and put everything back, I could have gone up to the menu and said, save as a default value. Let me just put it in default file 1. Then we could have sat here and let's look at the continuous wave again. We'll just leave it like that and said, well, now I want to go back and look at my original conditions. I come up here and I say, load default file 1. Okay, and it puts everything back in just a moment. And there, we have everything back automatically for us. So that's what those save and load default files are. You can load up to 5 of them. It gives you the ability to, while you're working on something, say, well, I want to look at something else, but I want to have to type everything back in. So let me save to a default file so I can load it back in quickly. I think that just about covers everything. Oh, one last thing. Let's say I was going to do some work on this laser. I wanted to set up a temporary class 4 control area. I need a barrier, so I'm going to set my barrier distance at 1.5 meters. Okay, and then come down here and take a look at my information. I want to look at the irradiance in 1 over E. So my barrier needs to withstand 417 watts per square centimeter, and it also needs to be able to withstand 41.7 joules per square centimeter. Okay, and so when you're dealing with repetitive pulse lasers, you need to look at both of those, because barrier ratings, really your barrier is rated for average power and for or irradiance and radiant exposure. So we need to look at both of those and make sure that the barrier can withstand not only the average power that hits it, but the energy or the peak power from the pulse that is going to hit your barrier. So I just wanted to point that out. Now, I think we're done. Okay,